So for this project, we will be designing a ROV, which is a remotely operated underwater vehicle, to enter in the May competition, which is held on June 20th to 22nd. It's divided into 3 sections, which is the Scouts for elementary, Rangers for high school, and then what we'll be participating is Explorers. Now, what is an ROV? ROV, what you see over here, is essentially just an operated vehicle from either a boat or the surface of where we're going to be operating a pool, which will be going under the water. It'll have cameras, sensors, thrusters, and it will all be, in essence, to finish a couple of tasks that the main competition is going to be giving us. So, ROVs previously have been used, were developed first for military use, is to seek and look out through the ocean floor in order to find lost missiles or to scout anything shipwrecks. Now, here's a couple examples of what ROVs look like. These are smaller types, of course. These don't have robotic arms or anything. They are usually with cameras, maybe a few sensors, and of course the light bulbs, because you know after a certain amount of depth, everything goes pitch black. Here are some inexpensive models, mostly made of PVC, of course LEDs, and they flow with a foam inside them. So for me, we'll be completing 4 tasks in a time frame of 25 minutes. First 5 minutes will be actually to prepare the system and put it in the water. The next 15 minutes is for it to dive in and complete the next 4 tasks, which is complete a primary node, install a secondary node. The second task would be design and construction and installation of a transmissal meter. The third task would be a replacement of an acoustic Doppler. And the fourth one is to remove a bit of biofouling, which would be on the structures and instruments which are going to be already placed underwater. And then for the last 5 minutes is to raise it up to the surface and be able to demobilize it. Now, the task will be able to be completed in any order we want, except that 1 and 3 have to be one after the other one.
This is the first design alternative that we considered. Some of the advantages of this design alternative is that it's easy to mount our thrusters right wherever we would want them. It's easy to find the center of gravity, and these 4 orange things are made out of woody material, which will keep the ROV upright in the water. But the main disadvantage of this design is that it's not very hydrodynamic, and it will create a lot of drag moving through the water, so it might take a little bit of time to get to our obstacles. The next design alternative is this one, which is pretty much the exact opposite of the other one, because it's very hydrodynamic and will be easily glide through the water, but the flotation material will be here while the counterweight will be at the bottom, which might not make it very stable in the water. So the proposed design that we decided to come up with is pretty much a crossbreed of both. And we will have the flotation material, which is this rectangular thing out of some weight material we haven't decided yet. We're going to install a cage around it where we can attach flashlights and the robotic arms to the bottom. And we will have 2 vertical thrusters on each of the wing components for ascent and descent. And we will have 2 horizontal thrusters for movement around the horizontal plane. Some of the design decisions that we were considering is the pool is only 15 feet deep, and the pressure wouldn't be that great at that depth, but for our team, we would like to reach in excess of 100 feet, which is about 58 psi, just for our use in the actual real world. Another decision we were come up with is the propulsion. We were deciding if we wanted to make either 2 movable thrusters that we could rotate about an axis, or if we wanted to just put fixed thrusters for every direction. And we're going to do 2 robotic arms for ours. Environmental impact. Okay. Our ROV will be operating at 12 volts, which is pretty much standard for automobiles and marines. That way we could implement it into whichever boat electrical system, or if we wanted to run it off a dock, we could just have a drop-down transformer and plug it right in. ROVs are beneficial in offshore drilling to install, repair pipeline, and drenching. For example, in the BP oil spill, the seating cap that was used to stop the leak was installed by an ROV. And the ROV will also be beneficial to the environment because it will help scientists collect data from the marine floor to further expand research. And here you will see a few pictures of it. This one's using a vacuum with a tube, and this one's using a cloud to remove samples.
Now, do we have a market outside of the US? Yes, we do. In fact, there's different types of categories. There's micro, there's mini, general standards, and then the working classes. Ours is going to be between mini and general, and it will be available for the public. Now, our manual labels and control will be available in several languages, of course. The power will be available in multiple adapters, as in American and European. Also, the specifications will be in US and Canada. This is an example of a working class ROV from the University of NTNU, used for biological research. Next. And now we have here working class from engineering. They are actually one of the leading manufacturers for ROVs and working class. Now, our project is going to be tested during the summer, and now that's our questions.
Okay, do you have any questions to that? You can ask any questions if you want.
How are you getting funding for this project?
Our pockets.
Your pocket.
You can. Yes, yes.
Have you thought about trying to get some kind of sponsorship?
MAID is an association with NASA. We are sending a few letters over, but for the moment we have no response. So hopefully that.
Because Lockheed Martin, they're up in Orlando, but they got a station in West Palm Beach. They do some kind of research with underwater submarines. You might just their love, maybe you might be
We're aware of that.
get something from them.
Thank you. Any other questions?
The question I wanted to throw out is, I see your design, and you said it was designed to be hydrodynamic by its nature, but I don't see the robot components or any of the other active components added to the system, and I would assume that you would need them there when you're doing that analysis. So my expectation is that you'll make sure that that's all designed into it. The robot probably, the arm on the robot probably ought to be designed so that it could be pulled in and be.
The thing about it is that we have to do a lot of testing in the summer, so right now we don't really have time to be testing the machines on our own time right now, but the machines will be included and tested.
And third, you'll be modeling this before you do the actual physical.
Yeah,
Yes.
we actually, if you notice, the robot, we added these, what seems to be a cage-like, and on the bottom, it has a bit of a clearance, and also two plates set in the right in front and the front and on the back. That is to place the robotic arms in order for it to seal in. Hold on. Again, we're testing on how big the robotics arm we want it. We're not, since the size of this is about 4.5, we don't want to make it that big, we want to make it portable. So the clearance is there, I left the clearance, it's just how we're going to develop the arm is left to be determined.
Okay, and obviously you gotta understand buoyancy, because if this thing doesn't weigh an awful lot, you might go down and try to pick something up and lift up your robot. So I think there's got to be a lot of work done there to make sure that you get in the contest and you're successful. That's key.
Yeah, Chip. Could you put up the previous slide, the one on your timeline? You said that your competition is in June.
It's, yes, it's
2014.
2014. So, anything else?
I'll go back to the analysis a little bit. How are you guys going to validate some of the models? And what are you, first off, what exactly are you using to model the fluid flow around your specific design? And how are you going to validate some of that analysis?
The Martin has a water tunnel that he's accessing us first to use. We're going to make a small scale model first to be able to test it on there. And probably make a small scale of the box alternative on the other one, compare results, and then from there we'll draw.
And what were you using, I'm sorry, what were you using to actually do the model?
Right now,
Okay.
With SolidWorks.
SolidWorks.
So you just solely created a model in SolidWorks, or have you done any sort of fluid analysis?
No, at the moment, we've done, by research and literary survey, we have read about and researched that it's having the smaller, because there are different types of categories of ROVs, going from micro, mini, and then the general working class. The bigger the working class, the more boxy it is, it'll move slower, and this is a time competition, so we wanted to cruise better on the water. Now, being the other, like the smaller types, some of them have movable thrusters, which allows them to move. I don't want to say like a fish, but they do have some that just move thrusters around, and the actual model can move in diagonal ways. Other than the bigger ones, they just go, ascend, and move to the side to side.
Yeah, go ahead.
So, any of you guys divers? I say, about buoyancy, neutral buoyancy. So, it is supposed to be a chips pointed that out, but are you planning on making this like a neutrally buoyant? Are you be able to adjust the buoyancy in this unit?
yes. The bottom of it will be able to mount counterweights for the flotation, so that once we're going to have fresh water since it's the pool, and then once we are able to distinguish the distance between point, we'll be able to even there for the competition.
So that'll be in a freshwater pool?
Yes.
The competition as well?
Yes. And if we want to use the salt water, we'll be able to add counterweights on the bottom to be able to.
One real quick last question. I see on your project timeline that basically your computer modeling is done, according to this. My expectation would be greater than what you're at with just doing the solid modeling. Expectation would be that you would create this with solid modeling, you do some kind of fluent software to simulate that this is going to be successful, that you don't end up in a situation where you aren't successful.
Regarding teamwork, how equitable was the task divided amongst the team?
Yeah, we split up the teamwork so everyone can have a part of it. Saying mostly the components of the ROV, saying buoyancy one side, and then somebody else is gonna pick like cameras and our Arduinos, and who has more knowledge. We just split it up, and depending on who has more knowledge of any of the units.
So it wasn't equitable then, it was equitable in terms of knowledge, not in terms of
Beneficial to each other.
Okay. All right, thank you.
When you, you said that the competition itself is in a 15-foot deep pool, but you're creating it for 100 feet. Any reason why 100 feet and not just stay within what the competition requires?
Because it wouldn't take that much engineering analysis at 15 feet, because the pressure wouldn't be that great. And for our own benefit to be able to use it outside of a pool in real life scenario, we would like to design it to be able to go 100 feet.
Okay, but do you think, from an economic standpoint, if you decide that you wanted to sell this thing, that building it for 58 PSI, is that really something that would be feasible to achieve, to sell? For example, if you were planning to sell it as a commercial product?
Well, on the market now, there's two companies that make commercial ones for divers and boaters to be able to inspect the bottom and floats and whatnot. They're rated for about 149 feet, and they go for about $5,000. So if we could achieve 100 feet within 50% of that price,